Now, in this example, what we need to do is we need to analyse the motion of an object which is being hoisted up into the air. Okay, so this crate in effect. And what we're required to do is just quote what the acceleration is of the crate. Okay, now we're going to be using a concept here which I introduced much earlier when we started to look at dynamics, which is this idea of a resultant force. Remember that actually, if I have a combination of forces that act on an object, then what the resultant force is the sum of these forces, and this is what goes into our Newton's second law. Okay, the overall force applied to our object characterized by a point mass. So this would then go in this term here. So what have we been told? So we have a crate that it has mass 100 kilograms. Okay, so mass of crate, that's important. Mass of crate is 100 kilograms. And this is being hoisted, this crate, up using a vertical cable. So I've drawn the diagram here. This is our cable. And this is our crate. Probably should move this a bit closer. Okay, and what is happening, and maybe just for realism, I have some sort of engine here. So this is an engine hoisting the crate upwards via the cable. So what we're told is that this cable has a tension inside it. Okay, so this is something that may be new to some people. Tension in cable is described by a force. And basically, this is the force in the cable. Transmitted axially along the cable. Okay, so it's transmitted where to? It's transmitted to the crate. It's transmitted to the crate in order to lift the crate. Remember, this has to overcome the gravitational force experienced by the crate. Okay, so in other words, overcome effects due to gravity. The effect due to gravity. Now, here, I said it's transmitted axially, so I'm making an assumption. The assumption is, well, there's two assumptions. Assumption one, what we'll do is we will assume that cable is aligned vertically. Okay. And the second assumption is, and this will become apparent after I mention it, is cable we treat as massless. Or light. Why? Well, because as soon as we start to embed mass and assume that this cable has some significant mass, then remember that when objects are moving as a result of the action of some force, then we know we have Newton's equations of motion. So this is this for the that we'll use for the crate at the top, and this embeds the mass of the object. And so we have to start incorporating what we call inertial effects, and this product here is our inertial effect. Okay, so we'd have to start considering this as soon as the mass of the cable, or which is linked to its density, was significant. So to eliminate inertial effects. Okay, so in this case, what happens is we need to consider forces. Forces applied to the crate. This is the message behind this example, because there's actually more than one force acting on the crate, which is different from what we encountered in the other examples. So if I add a page here, what we have is the following. There's our crate. This is zoomed up, if you will. Now, there is something I forgot to mention. Just for convenience, I'm going to put the axes. The motion is going vertically. I've highlighted this here. We have y and 0 on at ground level. Okay, it doesn't necessarily have to be like this. Remember, you can set this in any way you like. Here I have actually no information concerning how the initial state of the crate, and therefore, where I've set this axis won't actually come into play, where I've set the reference system. But it's just to keep in mind. So we have this somewhere here. This is our crate. And simply to get hold of the acceleration, we just need to balance the forces acting on the crate. Okay, so maybe I should label this appropriately. This is y, this is 0, and then just because I fancy myself as a bit of an artist, I'll do the lines representing the motion. Okay, motion is upwards. So now the motion of the crate is, and the direction of positive y are the same. And again, normally this is what I'm doing in problems like this. I normally tend to pick the reference frame to coincide with the direction of motion. Okay, so what about this balance of the forces? So we have forces. So what we get is, of course, we get the usual force that acts on the crate. So this is gravitational force. So again, this has magnitude mg, which is greater than 0. And we'll need to select the sign for this when we build this vector. So this is, hang on. So this is our vector representing gravitational force. Simultaneously, there is another force vector associated with the tension in the cable. I'm just drawing this on. So this is tension. The force applied, the axial force applied by the cable on the crate. Remember that this is the crate. And we were told the magnitude of this force was 1,200 newtons. That's our tension. So we have two forces. Again, you may say, well, why for heaven's sakes do we use vectors? The reason why I developed the approach in this way is because when you have many forces coming from all different directions, the idea of using vectors is important in capturing all effects. So actually, let me just do this. Ft, this will be the force due to tension. and then Fg will be the force due to gravity. So we're going to use the basis vector or the unit vector j to write down these forces because they're aligned with the y direction. The only difference is they have different directions themselves. So the first, the tension due to the cable, of course that has magnitude 1,200 newtons. However, well, we need to now consider what the sign of this is relative to our coordinate system. Now remember that the coordinate system, y, points upwards for positive. So if I think about designing a vector, for the tension, well, the tension also points upwards. Therefore, we just leave this as plus 1,200 newtons, with J embedded to represent the direction of this vector. And the second force due to gravity, well, we know this is mg. Magnitude mg, it's aligned with the vertical direction. So this is newtons. Last thing to do is to pick the sign to represent the direction. Well, this direction is pointing vertically downwards, as you can see in the diagram. As it does, gravity acts downwards, so we just introduce the minus because gravitational force opposes positive y direction. Now, very good. So next, well, what about the resultant force? Well, remember that the resultant force is the sum of the forces. It's the sum of the forces. I'll put equals sum of the forces. Sum of the forces. And so this gives us, hopefully I can finish before the battery runs out. This gives us the following: Ft plus Fg. That's all it is. And therefore, if we just plug these in, we will end up with the following vector. Okay, so that's our resultant force. And that is exactly what we need. So F, this was F. So F in our Newton's equation of motion is now this. And we'll put the numbers in a second. And so now Newton's equation of motion looks like this: md, or I tell you what, let's do this, F equals m dv by dt. Now, as usual, we'll take v to be vy. Actually, you know what? Okay, let's keep it like this. It's not necessary because technically this is our acceleration. This is what we want. Fine, acceleration is the derivative of the y component of the velocity. So this is our velocity. So then we have the following equation: 1,200 minus mg j sub in equals what? M dvy by dt times j. And of course, this can only be equal if the coefficients of the j's are equal. So this gives us our differential equation. Wonderful. So the last thing, don't forget that this is our acceleration. Okay, so we just need to rearrange this. so that we get the following. Divide by n. And what we get is this. All right, so what was m? Well, m was, I think, 100 kilograms. So let's write this in, 100 kg. And this implies our acceleration, ay. Oh, it's not a vector. Well, it's not a vector with ij's and k's. So our acceleration, which is the component of the acceleration in the y direction, which is the j component of acceleration, is as follows. 12 minus g. And of course, if you want to sub in this, which is the acceleration due to gravity on Earth, then of course what you see is this is positive, and this implies velocity is positive, crate moving upwards. Okay, so that's it then for the series of examples on one-dimensional motion. And next what we'll do is look at a problem involving a two-dimensional motion where we project objects. We fire objects at some angle relative to the ground. And you'll see that all the theory that we've done up to now will be applicable to this case and allows us to give a nice, simple representations for some physical quantities which occur in this problem. Okay, so thanks.